Okay, starting with chemical kinetics. This is simply the study of the speed or the rate of reaction. So you're looking at, we're doing still the same thing we did with thermodynamics, taking a little further and just looking at, well, how fast is the reaction actually occurring? And remember, thermodynamic favorability, that means spontaneous. Is it spontaneous or not? Does it happen by itself, or does it have to have some push? And remember from electrochemistry that if it is not spontaneous, if it doesn't happen by itself, then you have to have a battery. That's when you have your electrolytic cell. And another part to remember is that thermodynamically favorable, meaning that it's spontaneous, does not imply that it's rapid. It does not have to be fast. It simply means that it's occurring by itself. An example they give you is that diamond changing into graphite is thermodynamically favorable, but it's so slow that you would never notice it. So your diamond ring is not going to just disappear. And the main reason is because it has a really big activation energy that has to be overcome before that reaction can even occur. So it's going to take a very, very long time, millions of years, before that actually happens. So we're looking at several different things that we're going to talk about. We're going to talk about instantaneous rates. We're going to talk about the differential rate law. We're going to talk about the integrated rate law. We'll be talking about relative rates, activation energies, lots of different things. Talking about factors that affect chemical reaction rates. Remember, you're going to get lots of multiple choice question points from this section on what actually affects these. So, nature of the reactants is one of the things that affects the reaction rate. Some reactant molecules react in a hurry, others react slowly. Most of it comes down to the phase of the matter. Is that solids react more slowly than liquids or aqueous solutions. So physical state is extremely important. The more dense an object is or substance is, the slower its reaction. So if you have gasoline as a liquid versus gasoline as a gas, the liquid is going to be more dense. The gasoline as a gas is going to be less dense. So therefore, the liquid would react slower than the gas. Another reaction here, you've got K2SO4 as a solid plus B8NO32 as a solid. There's no reaction. But if you put both of those into aqueous solution, then the reaction would be very fast. So physical state matters a lot. Chemical identity, in other words, what chemicals are actually reacting, those are very important. Ions of opposite charge react very rapidly. Another thing you need to think about is the coulombic attractions between substances. That's what we're talking about with these ions. So this is where you're talking about opposites react. So you have opposite ions, positive ions, negative ions. They're going to react very rapidly because of coulombic attraction. The more bonds between the reacting atoms, the slower the reaction rate. And that's because there's more energy that is required to separate each one of those bonds. And so if you have substances with really strong bonds, these larger bond energies, they're going to react more slowly. Examples, metallic sodium reacts much faster with water than metallic calcium. Has to do with the bond sizes. Oxidation of methane can be increased with an increase in temperature. So temperature is another thing, and we're going to talk about that again in a minute. Photosynthesis, though, is very slow, changes very little with the increase in temperature because there's so many different steps in the pathway for photosynthesis. One of the things that with this whole physical state and why that matters is you have to look at your activation energy. So if we're looking at this whole thing that we talked about last time with thermo, where you have your reactants here, your products here, your energy of activation is right here, and it requires energy to break the bonds in a substance, and that energy, so back up, energy is required to break bonds, and energy is released when new bonds form. That's kind of a summary of your chemical identity there. Concentration of reactants. The more molecules that are present, the more collisions occur. So the more molecules you have, the more collisions happen. And the more collisions happen, the faster the reaction proceeds. So, example is when in between classes, the halls are extremely crowded, you're going to be bumping into people, it's crazy. And so you kind of get pushed along and shoved along down the hallway. If you go down the hallway during class time, when there's not very many people, then you go at your own little slow pace, however slow you want to go while you're texting on your cell phone. Temperature is another thing that really affects the speed. There's this great saying, heat 'em up, speed 'em up. You heat up the reaction and you're going to speed it up very quickly. So the faster the molecules are moving, the more likely they're going to collide, the more energy that's going to be transferred, and so molecular damage can happen. You're going to start breaking bonds apart because of the bumping into each other from the different molecules. And in that process, you'll break bonds and form bonds. An increase in temperature produces more successful collisions. So successful in terms of being able to overcome the activation energy and then in turn speed up the reaction. A general rule of thumb is that there's a 10-degree increase in temperature, it will double the reaction rate. So for every 10 degrees of temperature you raise a reaction, it's going to double the reaction rate. So that's a big, huge one for multiple choice questions on the test. This actually depends on the magnitude of the activation energy and the temperature range. So there's two things that are necessary for this. One is proper orientation, proper geometry or orientation. And number two, the second thing is sufficient energy. So in other words, the molecules have to be turned in the right way so that when they bump into other molecules, they can break the bonds or form new bonds. And you also have to have sufficient energy in the collision for the molecules to hit and break apart and form other bonds. Another thing that affects the rate of reaction is the surface area. You're talking about the exposed surface. So the more substances you have at the surface, the faster the reaction will occur also. So the greater surface area exposed, the greater the chance of collisions between the particles. So it goes at a much faster rate. So aqueous solutions are the ultimate exposure, though. If you get things dissolved, they definitely are have a very large surface area. Number 5 up here, adding an inert gas has no effect. Just the name inert should tell you. Inert means it's not reacting with anything. So it has no effect at all on the rate of the reaction. It's not actually in the reaction mechanism. This is a classic ruse with regard to test questions. In other words, they have a tendency to throw in this element or this compound is reacted with an inert gas and asking you how that will affect the speed of reaction. And the answer is it doesn't, because the inert gas does nothing. So they try to trick you there. So just be sure that you're aware that adding an inert gas does absolutely nothing for the reaction. A catalysis is an increase in the rate of the reaction due to participation of a substance called a catalyst. So a catalyst is not consumed. This is a very important thing to remember, is that a catalyst is going to be added into the reaction, so it's going to be with the reactants, but it's not used up. You can use that catalyst over and over again. It can participate in different chemical transformations, but basically it just goes in and it just speeds up the reaction. There are different types of catalysts. You have biological catalysts that are proteins called enzymes. So these are in our body. They're very shape specific, if you remember that from biology. It depends on the shape of the molecule. A good analogy that they use in biology is lock and key. But you can alter the pH or heat the enzyme, and that really disrupts the intermolecular forces that are holding those enzymes together. It causes the enzyme to denature, lose its three-dimensional shape, and therefore then it can no longer act as a catalyst. Catalyst is a substance that changes the rate of reaction by altering the reaction pathway. So some catalysts work by lowering the activation energy, which allows more collisions to be successful and the reaction rate is increased. The catalyst is not part of the chemical reaction, and it's not used up. Catalysts can be what's called homogeneous or heterogeneous. A homogeneous catalyst is in the same phase as the reactants. That's why it's homogeneous. Heterogeneous is in a different phase than the reactants. Homogeneous catalysts usually appear in the rate law because their concentration affects the reaction. So when we start talking about rate law, the homogeneous catalyst you will have to put in there. Heterogeneous, the concentration doesn't matter because it's in a different state. All right, collision theory. I'm just going to let you read over that. That's talking about this whole thing of what I was talking about the orientation and how the reactants bounce off of each other, but I'm going to let you read that one. Essential components of it, though, are that particles must collide. Typically, you have two of them. Two particles only collide at one time. And proper orientation of the colliding molecules is essential so that they come in contact with each other to form products in the right orientation. They must occur with enough energy to overcome the electron-electron repulsion from the valence shell electrons, and they also must have enough energy to transform that translational energy into vibrational energy so that they can rearrange and form new bonds. It's typically called an effective collision when that happens. The new collision product is at the peak of the activation energy. It's called the activated complex or transition state. And at that point, remember, it can either fall back to the reactant or go forward to the product. So once it gets up here at the transition state, it can go either direction depending on what's going on. So it can be forward, that would be a forward reaction coming to the product. It would be the reverse reaction if it went back to the reactants. Types of chemical reactant rates. The speed of the reaction is expressed in terms of its rate. The rate of a chemical reaction is measured by the decrease in concentration of a reactant or an increase in the concentration of the product in a unit of time. The concentration of the reactant, that is expressed in molar solutions, which is moles per liter, or an increase in concentration of the product is over a unit of time. So you have change in concentration divided by time. So the change in the concentration of the reactants over time. When writing rate equations, you can be written in terms of reactant disappearance, which would be a negative term, or product appearance, which would be a positive. So you are typically going to be given a table of numbers like this. So you're going to be given this data. It's going to tell you time. It's going to tell you the concentration of the products and the reactants. You may be given a table or a graph that looks something like this. And you're going to use the table and the graph to be able to answer some questions about reaction rates. Looking at instantaneous reaction rate, this is the rate at a given instant of time. So that's why it's called instantaneous. You probably know how to do this from math class, especially if you're currently enrolled in pre-cal. So you're going to look at the graph, you're going to know the shapes of the curves, and you will be able to find the slope of the curve. The slope of each line is drawn tangent to a given curve. So to determine the value of the rate at a particular instant of time, that is known as instantaneous rate, you simply compute the slope of the line tangent to the curve. Be sure that you are careful about this. So if we look at this reaction, you have NO2, change in NO2. You also have NO, and we have O2. Well, NO2 is our reactant, and we know it's a reactant because it is going down. It starts at a high concentration and it comes down. These other two, NO and O2, are our products because they are appearing. So we have this reaction that is going to be NO2 is going to break down into NO plus O2. And if we balance that, we should have a 2 there and a 2 there. So we're looking at this concentration of NO2. Well, let me go ahead and put that that's our reactant. That this and this, these are products. Okay, so these are being formed as this one's being consumed. we have time and we have concentration. And remember, concentration is just your molarity, so this is moles per liter. So if we look at this, and we look at the rate at a particular time, if we look and figure out the slope by doing, y'all all learn this in math, rise over run, which in this instance is the change of NO2 over the change in time. That is going to give us our rate. Okay, so this is our rate law. Just looking at our rate comes from the slope of this curve. Okay, so you can actually work that out. You could also get the we could figure out the rate for the product formation for both of those also, if we just work them out. Relative reaction rate is our second type. This one is expressed as a change in concentration per unit time. You should focus either on the disappearance of the reactants or the appearance of the products. So instead of looking at an instant in time, this is over a period of time. The rate of change of a reactant is always negative because it is going away, it's being used up. The rate of concentration of a product is always positive because it's being formed. And remember that relative here refers to the terms that relate to each other. So here is the exact reaction from the other side, the other page, of 2NO2 yields O2 plus 2NO. And if you look at this, okay, well, oxygen can appear only half as rapidly as the nitrogen dioxide disappears. And nitrogen monoxide appears twice as fast as the oxygen. So there's 2 moles of NO to 1 mole of O2. Be sure to keep in mind what your algebraic signs are going to be. That they're going to be negative for the reactant because they're disappearing, and positive for the products because they are appearing. So if we look at this, the initial rate of reaction is equal to 1/2 of the change of the concentration of NO2 over delta T. It's also equal to the change in the concentration of O2 divided by delta T. And it's also equal to a positive 1/2 change of concentration of NO over delta T. So you can actually change those by multiplying by 2, but really that really gets more complicated. So I would just keep it as a fraction. Here's another one. Write all the relative terms. You've got 4pH3 yields P4 plus 6H2. So negative 1/4. So you're just putting it in a fraction. 1/4 equals plus the change of P4 over delta T, because 1/1. So this is 1/4. This is 1/1 because there's only one of those, and 1/6. 1/6 delta H2 over delta T. It is okay to shorten the initial rate of reaction just to rate, because that's perfectly fine. And you can read the rest of that if you want to about you can change it out of a fraction, but to me that's just a lot of steps for no reason. Last thing is exercise 1 here. It says write the relative rates of change and concentration of the product's reactants in the decomposition of nitrosyl chloride, NOCl. So we just make this as a fraction, and that's 1/1. So we have rate is equal to, this is our reactant, so that's a negative 1/2 of the change in concentration of NOCl over delta T. It is also equal to 1/2, and that time is a positive half. The change in concentration of NO over delta T. It is also equal to just the change in concentration of Cl2 over delta T. If you notice, everything is over delta T. These are equal to each other because rate is equal to any part of that reaction, not just a part. We will pick up tomorrow with differential rate laws in class.